This is Chapter 9, Estimating the Value of a Parameter, also known as confidence intervals. So I'll be referring to this chapter as the confidence interval chapter, and this textbook calls it Estimating the Value of a Parameter. Before we get started, if you could find the slide from Chapter 8 that has all the information about means and proportions on it, we'll be needing of this page of information while we go through Chapter 9 and also as we go through Chapter 10. So if you could find this page from the Chapter 8 material before we start. Alright, so Chapter 9 is about confidence intervals. We'll kind of talk about in general what a confidence interval is, and then we'll be estimating using those confidence intervals for a proportion, and then this section 9.2 is about for the same idea for a mean. So the idea of a confidence interval, if we want to estimate the proportion of adult Americans who believe the amount they pay in federal income taxes is too high, it would be unreasonable to expect that we could survey every adult American. Instead, we use a sample of adult Americans and arrive at an estimate of that proportion. And we call this a point estimate. So our sample statistic that we get, whether we get an average or a proportion, or maybe we're getting a standard deviation, whatever we get, whatever sample statistic we get, we now call a point estimate. So a point estimate is the value of a statistic that estimates the value of a parameter. So the whole purpose behind sampling is so that we can approximate or estimate the value of the true proportion or true mean or whatever we're looking at. For section 9.1, we're looking at true proportions, which is p hat, back from, I believe that was in chapter 8. P hat is x over n, so we have desired over total, which is either a ratio or a percentage, just like Chapter 8. So if we took a sample of 1,020 adult Americans and found that 490 answered yes to that question about believing that the federal income taxes we pay is too high, what would be our point estimate for this parameter? P hat would be x over n, which is the 490, over 1,020, which is approximately about 48%, or 0.48, or 48%. So we can represent this as a decimal, as a ratio, or as a percentage. All of these mean the same thing, and they're all considered proportions. So it's just that easy, nothing complicated about it. So we know samples are not exactly accurate, so it's important to have what we call a cushion around our point estimate. So we know it's not going to be exactly 48%. The true population proportion will not be exactly 48%. It will be around 48%. So if we took 50 different samples of these 1,000 adult Americans, they would most likely all have different point estimates. So every time we took a sample, we'd probably get a different point estimate, but hopefully they'd all hover around 48%. So a confidence interval gives us a range of values that we feel the true proportion or mean is within. So we have our point estimate, and we can go a little bit above that and a little bit below that to make our cushion or our confidence interval about where we feel the true proportion might be. So that's what a confidence interval is. To get the idea of how confidence levels work, I want you to think about, on a scale of 1 to 10, how confident are you that you can guess my age within 10 years? So you've never met me, and you don't know what I look like, but you hear my voice, and maybe if you could just guess, would you be accurate within 10 years? Most of my students would give that rating an 8 to 10. On a scale of 1 to 10, they're fairly confident they could guess my age within 10 years. What if I wanted you to guess my age within 5 years? So I want you to be more precise. While that 8 to 10 range generally goes down to about a 5 to 7. You're less confident that you can guess my age within 5 years. I'm giving you a smaller cushion, a smaller window, so your confidence has gone down. How confident are you that you can guess my age within 2 years? Well, again, Most students' confidence goes down even further, somewhere between a 2 and a 4. They're getting less confident as I'm decreasing that cushion. And how confident are you that you can guess my exact age? Most students say between a 0 and a 1. So they're not very confident they could guess my exact age, but they're fairly confident they could guess my age within 10 years. So as we decrease our cushion, our level of confidence also decreases. So if we want to increase our confidence, we have to increase what we call the cushion. If we want to decrease our cushion and be more precise, we would have to decrease our confidence level. So when doctors try to estimate when a baby's going to be born, they usually give you a window of when the baby might be born, and everyone's always concerned about the exact due date of that baby. Well, the doctor cannot be very confident of that exact due date. It's actually a guess. But he can give the mom a range of values at a lower level of confidence. It can give them a bigger range. He can give them a bigger range of values and be more confident. So you have the exact guess. A lower level of confidence would give you a smaller interval, and a higher level of confidence would have to have a bigger window or a bigger cushion. So we have these different levels of confidence, and some of the most common ones are 90%, 95%. Sometimes we want to be 99% accurate. So a 95% level of confidence, which is the most generic one, implies that if we took 100 samples and got all their different confidence levels, all the different confidence intervals were created, then about 95 of those 100 would contain the true mean, and 5 of them would not. So it would be about 95% accurate. So confidence intervals are constructed using the point estimate from the sample, plus or minus what we call the margin of error, which you might have heard of before. And the margin of error is related to the standard deviation. So the larger the standard deviation, the larger the margin of error. The smaller the standard deviation, the smaller the margin of error. So we'll see exactly how this works in just a minute. In order to compute a confidence interval, we need to have the exact number of standard deviations for different percentages of confidence. So remember on a normal curve, 95% of the data fall within approximately 2 standard deviations. This is from the empirical rule. And that's a guess, that's an approximation using the empirical rule. If we were to exactly calculate that 95% of the data, they fall within 1.96 standard deviations, which is pretty close to 2, but not exactly 2. So if we have our bell curve, we know that 95% of our data fall in this range. It's about it's exactly 1.96 standard deviations above the mean and 1.96 standard deviations below the mean. That leaves 2.5% outside the range up top and 2.5% outside the range on the bottom. So 95% is in the middle. We have 2.5 up top and 2.5 up bottom. We get that number from doing 100 minus 95. That gives us 5. We split that evenly between the lower tail and the upper tail. And that's where we're getting 2.5%. So 2.5% of the data fall below that and 2.5% above that. So remember, everything is symmetrical. On bell curves or on normal curves. Everything is symmetrical, so you can always divide by 2 to get the amount in each tail. So we're going to do that same exercise with different levels of confidence, and then I'll show you where you can find these answers if you forget them. So if I want to be 90% confident on my bell curve, that means I want 90% of my data to fall around the true mean. So here's the true mean or the true proportion. I want 90% of my data to fall within that range. That leaves 5% in the upper tail, and that leaves 5% in the lower tail. I'm getting that number from doing 100 minus 90, which is 10, and dividing that equally between the tails. So 5% up top and 5% on the bottom. So that is 0.05 as a decimal. To get what they call a critical value, we're actually looking for the z-score corresponding to the lower tail. I'm actually looking for the z-score right here, right where 90% stops on the lower tail. So what I'm going to do in the calculator is do inverse normal, which we did back in chapter 7, of 0.05. If I do that, that is under second vars inverse normal of 0.05. That gives me negative 1.64, and I'm going to round that off to 5. Well, we don't need to worry about the negative for the critical value. You just ignore the negative, and our critical value is 1.645. That tells me the z-score that separates the middle 90% from the top 5 and the bottom 5%. So a 90% level of confidence corresponds with a critical value of 1.645. And again, they use the notation z, and then they call this number alpha over 2. Alpha is the leftover, and we're dividing it by 2. So down here when I did 100 minus 90, 10 is the leftover, and so that would be your alpha, and then divide by 2 to get 5. So I just say half the leftover, but the textbook uses the notation alpha over 2. So it's looking for the z-score of alpha over 2. I know that notation looks a little messy, but that's what it's asking you to do. So let's try this again with 95%. I'm going to change colors. Hopefully it'll make it a little easier to see. So for 95%, again on the bell curve, that means I want 95% of my confidence intervals to be in the middle, around that true proportion or true mean. If I do 100 minus 95, that leaves me 5. Divide that by 2. We did this earlier. That leaves 2.5% in the upper tail, 2.5%, and also 2.5% in the lower tail. And I'm looking for that z-score at the lower tail. So what I'm going to do is inverse normal. I always have to convert my percentage to a decimal, which is why they have 0.025. And if I do that, 0.025. So you can hit second enter, or you can go back to second vars. Again, ignore the negative. That's where they're getting 1.96. So that rounds off to a 6. So that's the critical value corresponding to 95% confidence. And we can do that one more time. For 99% confidence. Again, these are just the most common levels of confidence. You can do this with any level of confidence. These are just the most common. So if I have my curve, I want 99% of my confidence intervals to fall around the true proportion or the true mean. 99% in the middle. That only leaves, let's see, 100 minus 99 is 1. Divide that by 2. That's 0.5, so it's 0.5% and 0.5%, which is 0.005. So it gets very particular. Inverse normal of 0.005. Second var is option 3, 0.005. Gives me, ignore the negative, 2.57. I think the textbook puts a 5. That really is a 6. It'll give you roughly the same answer, so it's not the end of the world. But that rounds technically to negative, just 2.576. You don't need to worry about the negative. So each confidence level corresponds to a particular critical value. So each level of confidence will have its own critical value. Now there is a chart in the back of your, or at the end of your formula booklet. So if you turn in your formula booklet to the end, I believe it's table 5, where we're looking up the normal values, the probabilities with the particular z-scores. Below that, you have this little chart in the corner, and it gives you 4 common levels of confidence. So 90, 95, 98. and 99, and it tells you the critical values for those. Now, if your homework asks for a different confidence level, you'll have to do inverse normal of half the leftover to get that value. But those four in that little chart are the most common that you'll see, and those are the corresponding critical values. So you're going to need that critical value in the formula for confidence levels. So computing the confidence intervals for sample proportions. I got this chart out of your book. Each confidence interval has a lower bound and an upper bound because it's an interval. You take your point estimate, and you add or subtract. So one's subtract and one's add, so I just put them together, add or subtract. What we have is the critical value. So that's the z alpha over 2. That notation is the critical value, the numbers we just figured out, times this crazy formula. This is the standard deviation that we learned in chapter 8. So this is the standard deviation for proportions. So back in your formula booklet, if you turn to the second page at the bottom where it says chapter 9, you'll see the formula right there. And it has the plus and the minus at the same time. The textbook separates them, but the formula sheet puts them together. So z of alpha over 2 is the critical value, and there's the standard deviation for a proportion, which you can see right above it in chapter 8. It's the same thing. So point estimate plus or minus the critical value times the standard deviation. This formula looks really crazy. You don't have to ever crunch the numbers by hand. I do expect you to know how to set it up, which piece goes where. But as far as actually getting the answer, the calculator has a formula to do that for us. The same conditions are true that were true in chapter 8. N times P times 1 minus P must be greater than or equal to 10, and the sample must be less than 5% of the population. So those two conditions are still valid. Those are the conditions we wrote down on that same chart back in chapter 8. So all of those conditions are still true. So we can do this purely by hand or in the calculator. Most students prefer the calculator. If we're going to do this by hand, we have to compute the value of p hat, which remember is x over n. Verify normality, which I don't overemphasize here. That's the n times p times 1 minus p is greater than or equal to 10, and the sample is less than or equal to 5% of the population. So those two checks verify normality. Then you find the critical value for the particular level of confidence. You can look it up or use inverse normal. Then you plug everything into the formulas for the lower and upper bounds. So that's how to do every step by hand. If you want to use the calculator, you still want to calculate the value of p hat. Verify normality, those same two checks. I do expect to see the formula set up. There are some homework problems where it just wants to see the formula set up. And then in the calculator, if you go to stats and then tests, there's an option that says 1 prop z interval. So that's under stat, and then over to tests, and it's down a little bit. Mine's option A. 1 prop stands for proportion, z int stands for interval. 1 proportion z interval, so it's option A in the TI-84s, option A. So there is an option, and it will ask you for all the important values, and we'll practice that in just a second, and it will crunch all the numbers for you. Alright, so let's see an example. This is from page 397. It says 800 randomly selected driving teenagers were asked if they ever text while driving. 272 of them said yes. Obtain a 95% confidence interval for the proportion of teens that text while driving. So we want to compute the value of p hat. That would be 272 out of 800. This is what they call x, and this is what they have as the sample size n. we want to make sure that normality is checked. I'm just going to do this check since we don't know the population size. So our sample size is 800. Our proportion, we would have to do 272 over 800 to get that number, which is 0.34. So 800 times 0.34, and then we would do 1 minus 0.34, which is 0.66. Multiply that all together, which is 179.52, and that just has to be greater than or equal to 10. That's the only check that we need to worry about since we don't have the population size. So we found our p-hat, we checked normality, now we can use the calculator or crunch the numbers by hand. I'm going to set it up by hand, and then I will show you how to put it all in the calculator. So we start with the point estimate, which for this situation was 0.34, plus or minus the critical value, z of alpha over 2, which for 95%, we can look in our chart. Let's see, back on that last page 14 of the file, at the very bottom, we look up 95%, and it's 1.96 is the critical value. So 1.96 times the standard deviation formula, which is 0.34, times 0.66 over 800. Now again, there are some homework problems that just want you to be able to set it up. I don't expect you to type all this in and get the answer. I just want you to go to stat and then test 1 proportion z interval. Interval. And let's see what it wants. So stat tests down to 1 proportion z interval. It wants x and n. It is going to calculate p-hat for you, so it wants x, which is 272, and n, which is the sample size 800, and the confidence level, that's all it needs. You hit calculate, and it spits out your p-hat and your interval. So the answer would be 0.30717 to 0.37283. Now that doesn't really mean much right now. Putting this all together in context, we would say we are 95% confident that the true proportion, so we're 95% confident that the true proportion of teens that text while driving is between, and we would round this off, so 0.30717 is about 31%, and 0.37283 is about 37%. So that's kind of putting it all together. We are 95% confident that the true proportion of teens that text while driving is somewhere between 31% and 37%. So we'd round these off to make a concluding statement to answer the question. All right, so let's look at another example. I'm going to get out a separate sheet of paper for this one so you can see everything better. This is out of the book on page 402, number 29 in the exercise section. It's about tattoos. It says a Harris Interactive poll conducted during January of 2008 found that 944 of 1,748 adult Americans 18 years or older who do not have a tattoo believe that individuals with tattoos are more rebellious. I know these situations are a little silly. The author of this textbook actually has his students go take polls and do surveys, so these are actually real sets of data, even though the scenarios are kind of silly sometimes. So we're going to obtain a point estimate for the proportion of adult Americans without tattoos who believe individuals with tattoos are more rebellious. So this is number 29 from page 402 in section 9.1. So part A, p-hat is the point estimate. That's 944 out of 1748, which is approximately 0.54 4, the rest are 0. So that's about 54% believe that. Part B, verify the requirements for constructing a confidence interval are satisfied. So we're just going to do n times p times 1 minus p and make sure that's greater than or equal to 10. So our sample size is 1,748. Our p-value is 0.54. 1 minus that would be 0.46. And let's see what that gives us. 434.2032. As long as that's greater than or equal to 10, we are good. That's verifying the requirements. Part C, construct a 90% confidence interval for the proportion of adult Americans who believe people with tattoos are more rebellious. So again, I like to see the setup. That would be 0.54 plus or minus the critical value for 90%. If we look on our chart, too close, sorry. 90% will be 1.645. And then the formula for the standard deviation is 0.54 times 0.46 over the sample size. Now you don't have to actually work that out. We can just let the calculator do the work for us by going to Stat, Tests, down to 1 prop Z interval. This time our X value is 944. Our sample size is 1748. Our confidence level is 0.90. And we'll go to calculate. That gives us 0.52. I'm going to round here to 0.56. So that'd be about 52% to 56%. And part D, construct a 99% confidence interval for the proportion who believe people with tattoos are more rebellious. Everything stays the same except for the critical value. For 99%, our critical value is larger, 2.575. And the standard deviation formula is the same. And we can again use 1 prop Z interval. Oops, stat test down to option A. Same values, but now we want a 99% confidence level. And we get, I'm going to round here, 0.51 to 0.57. So it was 52 to 56%, now it's larger, 51 to 57%. This is a wider interval. So part E asks, what is the effect of increasing the level of confidence on the width of the interval? Increasing confidence increases the width of the interval. So there's the fully worked problem. Increasing the confidence increases the width of the interval. If you want to be more confident, you're going to need a wider range of values. So there is that problem fully worked out. I'm going to pause there and then I'll continue in just a minute.